In this video, you will learn how to correctly draw resonance structures and what is a resonance hybrid. So when we consider drawing resonance structures, let's look first at an example. An example is acetonitrile anion. We start with structure on the left, so deprotonated acetonitrile anion, and then we can draw resonance structure on the right simply by pushing electrons as indicated by curved arrows. And we can see that this species involves delocalized electrons and that there are two resonance structures. Question is, how did we know that there were delocalized electrons in this anion in the first place? And how did we come up with two and only two resonance structures? Why there are no more? Why we don't have 3, 4 or more? So to be able to correctly draw resonance structures in any species, we have some rules and you need to be familiar with them. First important rule is that atomic nuclei and single bonds must remain in fixed positions. Here we have example of acetone and propene 2-ol. Note equilibrium arrow between the two species, unlike resonance arrow. Resonance involves only electron delocalization. So in this example of acetone vinyl alcohol equilibrium, two forms of a compound differ not only in position of their electrons, but also in the position of hydrogen atom. So those are two isomers. In this case, this type of isomerism is tautomerism, so these are two tautomers. So these are two different molecules. This is not resonance, this is equilibrium of two different isomers. And so this also illustrates how to correctly use resonance arrow and equilibrium arrow. In the first example of acetonitrile anion, we should use resonance arrow because that's electron delocalization within the same molecule. In the second example, we have to use equilibrium arrow because those are two different molecules, two different species, and we have equilibrium between the two. So if any nucleus moves, that's not resonance, that's equilibrium between different species. Only electrons can move in the course of electron delocalization. The second rule states that only non-bonding electrons, and those are free electron pairs and unpaired electrons, and pi electrons are capable of electron delocalization or resonance. The best way to formulate that is that only p and pi electrons can participate in resonance. And that also means that free electron pairs and unpaired electrons must be in atomic p orbitals to participate in resonance. Now, these first two rules don't apply to special cases such as hyperconjugation and delocalization that involves carbon-carbon bonds of cyclopropane, but we are not considering those in this video and in fact in this chapter. Now, if we consider application of this second rule, how are we going to draw resonance structures? Pi electrons move only towards a positive charge or toward another pi bond, and non-bonding electrons only move toward a pi bond or a positive charge. And here are some examples where we have a pi electrons moving towards a positive charge. That's allyl cation. Also, this means that an sp3 hybridized carbon cannot participate in resonance. So presence of an sp3 hybridized carbon is going to prevent electron delocalization. So in the first example here, we have free electron pair on nitrogen and then neighboring pi electron system of benzene. But there can be no electron delocalization between them, between free electron pair on nitrogen and that pi system, because there is an intervening sp3 carbon, and that prevents electron delocalization. In the middle, we have free electron pair on oxygen and positive charge on carbon. But again, there is an intervening sp3 hybridized carbon, and that prevents resonance. Finally, in the third case of compound without resonance stabilization, we have two double bonds that are separated by an sp3 carbon. Because of that sp3 carbon, two double bonds do not exhibit resonance stabilization. They do not exhibit electron delocalization. On the other hand, we have three examples of resonance underneath it. So when all the carbons that are involved are at least sp2 hybridized, and that's most common case, they could also be sp, but sp2 hybridized, then we do have resonance stabilization. And so you can see how in the example on the left, free electron pair moves towards a pi system, a double bond. Example on the right, or in the middle, sorry, free electron pair from oxygen moves to form a double bond between itself and carbon with positive charge, and in the third case, free electron pair from oxygen moves towards a pi bond. The total number of paired and unpaired electrons should remain the same in all the resonance structures, all the individual resonance structures. Here is an example of benzene. So on the left are two correct structures where there are two structures with no unpaired electrons. On the right are structures that are not acceptable. It is not acceptable to homolytically break a double bond to generate additional resonance structures with unpaired electrons. Those would be much higher energy structures, and they don't contribute to resonance hybrid. Now, this rule is somewhat flexible, and there are exceptions. For example, in case of 1,3-butadiene, a structure on the right with unpaired electrons sometimes explains reactivity of 1,3-butadiene quite well. And in some rare instances, such as 1,3-cyclobutadiene, a structure with unpaired electrons is actually more accurate compared to one with two double bonds. Still, you should consider that in an introductory organic chemistry course, this rule always applies. So you should not be generating any structures with increased number of unpaired electrons. All the atoms that are involved in electron delocalization must be planar or be close to planar. The reason for it is that only if all the atoms are planar, orbitals can properly overlap for electron delocalization. If atoms deviate from planarity, that prevents orbital overlap and prevents electron delocalization. An example of a molecule where electron delocalization is prevented is molecule of cyclooctatetraene. Because it is puckered, it is in a boat conformation, it is not planar, and electron delocalization is not possible. A resonance hybrid is supposed to represent the actual structure of the molecule. A resonance hybrid is a combination of the individual resonance structures. If all of the individual resonance structures are equivalent, then each structure equally contributes to resonance hybrid. But if they are not equivalent, then more stable structure contributes more to the resonance hybrid. And of course, then we need to be able to identify which structure is more stable and which one is less stable. A structure with more pi bonds is more stable. Another more obvious way to state that is that structure with charge separation is less stable compared to one without it. Because the only way to generate fewer pi bonds is to heterolytically move electron pair to one of the atoms of the double bond, and that results in charge separation. So if you consider an enon, structure on the left is less stable because it involves charge separation and, of course, only one pi bond. One on the right does not involve any charge separation and has two pi bonds, so it is more stable. Resonance hybrid will be a combination, of course, of the two structures, but it will more resemble structure on the right than one on the left. A structure in which all atoms have complete valence shells is more stable compared to structure with empty orbitals. And here we have an example of protonated carbonyl group. Less stable resonance structure is one in which carbon carries formal positive charge. That's because carbon has only 6 electrons. It has an empty orbital. Much more stable structure is one in which oxygen carries formal positive charge. That may be a little bit counterintuitive because oxygen is more electronegative than carbon. But in this structure, all of the atoms have octets filled. So again, resonance hybrid will be more resembling, will be closer, will be a combination of the two, but will be closer to the more stable structure. One in which oxygen carries formal positive charge, but all atoms have complete octets. Finally, structures in which atoms have an unnatural charge are less stable compared to those with natural charge. Natural charge means that electronegative atoms have negative charge, electropositive atoms have positive charge. Again, if you look at first example of xenon, we can actually come up with another relatively reasonable resonance structure, and that's the last one on the right, in which carbon would have negative charge and oxygen positive charge. This structure is very high energy because charges are unnatural, carbon negative, oxygen positive, and for that reason its contribution to resonance hybrid is very small. It does contribute to resonance hybrid, but contribution is so small that we usually ignore it and assume that a resonance hybrid of an xenon is only combination of the two structures on the left. Now we are going to look into several examples of resonance hybrids. So here we have first two examples. One on the top is methyl vinyl ether. Structure on the left is a lower energy structure, and one on the right is high energy structure because of the charge separation and positive charge on oxygen, while we have negative charge on carbon. So structure of methyl vinyl ether will resemble much more one on the left, much less one on the right. Nonetheless, structure on the right is important because it contributes to resonance hybrid, and sometimes reactivity of methyl vinyl ether is explained quite well with structure on the right. In the second example, we have an xenon, slightly different xenon from one that we have just seen, but again, there is one high energy structure, and that's structure in which oxygen carries positive charge, carbon negative charge, and as I already explained, we usually ignore that structure and consider only remaining two structures when we are considering what resonance hybrid looks like. And of the two remaining structures, one in the middle is lower energy, so it will contribute more to the overall resonance hybrid. Then, when we consider these three examples, first an example of enolate anion, very important reaction intermediate. In case of enolate anion, high energy structure is one that has negative charge on carbon, while lower energy structure is one with negative charge on oxygen. That's because oxygen better tolerates negative charge due to its high electronegativity. Still, sometimes we use structure on the left to explain reactivity of enolate anions. Structure on the right contributes much more to the overall resonance hybrid, but hybrid is combination of the two. In case of esters to the right, this is carboxylic acid. In case of a carboxylic acid on the right, high energy structure involves charge separation. So that one contributes much less to the overall resonance hybrid, and structure of carboxylic acid is mainly represented by formula on the left. One on the right is much higher energy structure. Finally, at the bottom, we have two structures of anion obtained by deprotonation of carboxylic acid. Now you can see that two structures are equivalent. And when structures are equivalent like this, then they equally contribute to the overall resonance hybrid. So resonance hybrid is exactly 50-50 contribution of each of the two structures and is exactly halfway between the two. Next example is that of 1,3-butadiene. We have seen that one already several times. And now we have three resonance structures. Following rules we have covered already. We can move double bonds towards each other, as shown by arrows on the top to the right or to the left. Arrows on the top, movement of arrows, top curved arrows generate resonance structure on the right. Bottom movement generates resonance structure on the left. So the actual resonance hybrid is a combination of all three structures. Of course, the middle structure is the lowest energy, the most stable, so it contributes the most to the overall resonance hybrid, but the other two also have considerable contribution. Note, when terminal carbons are considered, in each structure, each terminal carbon is in one structure positive, in one neutral, and in one negative, which means that they don't carry any partial charge. Another very important example is that of amide. Amides are somewhat unique in that nitrogen has a free electron pair, and because of the somewhat lower electronegativity compared to oxygen, it is a good electron pair donor. And for that reason, the resonance structure on the right has considerable contribution to the resonance hybrid. because structure in which nitrogen carries positive charge and oxygen negative is actually not that high in energy. And so even though still structure that does not have charge separations on the left is lower in energy, one on the right is not that much higher in energy. So resonance hybrid is closer to being somewhere between the two than resembling mainly one structure. And amides are known that for their unique properties, in that carbon-nitrogen bond is partial double bond, and it has been experimentally observed that there is limited rotation about that bond because it is a partial double bond. This next example is a representation of resonance in benzyl cation. So positive charge is delocalized over carbon atom that is outside the ring, methylene carbon, and carbons of the ring that are in position 2, 4, and 6 relative to methylene carbon. There are 5 resonance structures, and they are of about the same energy. So each of those 5 structures has approximately equal contribution to the overall resonance hybrid. We can represent overall electron distribution and distribution of positive charge by one structure on the right. Again, as discussed before, this is not preferred representation. We usually like to represent all the individual resonance structures, or just represent one and assume that trained chemists would know what the others are. But structure on the right shows a location of partial positive charges, that it is located on the methylene carbon and carbons 2, 4, and 6 of the ring. And of course, partial positive charge is indicated by symbol delta plus. And then there is resonance in benzyl radical. So benzyl radical has equivalent resonance structures to benzyl cation, basically equivalent 5 resonance structures. Again, they are about the same in energy and have equal contribution. Note that this time we are using, of course, fishhook arrows or half arrows to represent movement of single electron, and individual double bonds are homolytically cleaved to generate new resonance structures. Partial free electron is indicated by delta dot, so that may be something new to you. So partial free electron is localized, or actually delocalized, in positions 2, 4, and 6 relative to methylene group, and of course on the methylene group. So that's indicated with formula on the right with symbols delta dot. This completes our review of resonance structures and resonance hybrid, and next we are going to look into chemical consequences of electron delocalization.